Welcome back. It's been a while. My apologies for the last 2 weeks. Uh, Life got in the way, and then more work got in the way. So work, work, work. But we're going to finish up the semester strong. I have a few announcements to begin with. First, the course evaluations for the course are available in Icon. You probably know how to do that, but just in case, here's some steps. Go into Icon, go to the dashboard, and click on Spot. You can do that whenever you want. You can do that while I'm talking. Heck, you could even provide vote early, vote often, rate me. No, I'm just kidding. I do appreciate any information you can give me about the class. I do take it seriously. I know this class has been a bit of a challenge to teach this year, my first time through it. So your feedback will be especially important to try to make it better if I ever am to teach this again. I mean that seriously. So please consider voting, voting, rating, providing your opinion. Okay, number two, I think I mentioned this over email. We're not doing any chapter quizzes. We're all done with those. The bulk of the class, the thing I talked about at the beginning, the three methods, maximum likelihood, Bayesian, and multiple imputation, were really the core. And thankfully, we've made it through that. You have a homework on multiple imputation now that's due next week. So we're not going to do any more chapter quizzes. I'm going to try to squeeze in as much information from a theoretical perspective before you leave class this year. So we're going to try the best we can to get the rest of this in. Um, Once again, I mentioned homework five is due next week. This is the one where you're generating your own missing data and then filling it in with multiple imputation. I was hoping that this will be a guide for you because, again, it's hard to do missing data. Each one of you has a different context for your data sets, right? So I was hoping that maybe this will give you some practice with data that look like a little bit more like yours. But if you have any need for help or whatever, just send me an email. I know office hours are past. Today was office hours. I was spent yesterday. I had to move my office hours. You saw the email because today my son had a performance at his elementary school. So fourth grade singing. That's probably the last performance he's going to have. So I had to be there. So I hope you don't mind. Uh, Kind of important, at least for me and to him. So, any questions on homework five? How many of you've done homework five? What would you say your experience with multiple imputation was compared to the other methods? What was that? Frustrating. Oh, yes, you spent a number of hours with Levon. Yeah, yeah, I believe it. Oh my goodness. Right. Oh no. Yeah, that's where notebook files break down. Yes, but yeah, that's tough. What about the rest of you? Do you have any? What do you feel about multiple imputation versus maximum likelihood or other Bayes? Oh no. You were very eager. Yes. Yes. I should have given some guidelines to not have that many. I apologize to you. It's okay. Yes, I understand now. I apologize. Uh, Ikyung, did you have a okay time with multiple imputation? Or actually, you had it hard because you're doing network psychometrics with missing data and everything went crazy, right? Yeah. Okay. Yeah, it's interesting because the models that you're working on do change equations, right? That's their estimation trick. And so you think that there would be a way to leverage that already to do a better job building imputations in, but maybe that's an area for research. Something that you can think about. JC, did you have an okay time with imputation, or was that hard? Oh, good. That's fine. That's fine for right now. I don't know that. Well, we're going to talk about multi-level today, and I don't know that we're going to have some great answers for it, but I have some more strategies. But it's fine for what you've done for the class. That's not a problem at all. No. All right. Well, those of you who haven't, just heed the warnings. It takes a while to do the missing data. I thought so when I made the homework, and I made my example in the homework, at least my example for class, where I ran the mice and the what was it? Levon, MI Levon, or was it SEM tools? I can't remember which package it was that sort of put everything together. I found that to be way easy compared to like almost everything else we've done up to this point. But I think that just depends on the type of modeling paradigm you're in. If you're in an SEM framework, putting that in quotes, and you can do things in a package like Levon or M plus, it's already been built in for you. But if you're not, you sort of have to build it yourself, network psychometrics or so forth, right? And that becomes a bit of a challenge. So um, interesting to think about it. I personally felt like I'm sort of in between, like my own concept of trying to do this is somewhere between the I like the agnostic approach to multiple imputation, or and I would really prefer an agnostic approach to estimation, but that's hard to really build in. So I don't know how that would work out. Excuse me as I show you my email there. All right. Any other thoughts on homework five? Yeah. Yeah. It is hard. Yes. Hmm. Right. You don't, right? And so I think that the thing about it is, and this is where if you're taking a class like Lisa's advanced multi-level advanced longitudinal she's teaching, right? She teaches a little bit of the multivariate multi-level models, which a lot of people call multi-level SEM. Again, I'm not a I'm not of that ilk, but the bigger picture is if you think of each one of the variables, particularly when you have level one predictors, right? So that where you might have level two variation of those predictors, I think you have to start thinking of those more as their own multi-level models, right? And so you build basically multi-level models for all of your outcomes that are level one, including Y and any X's you have. And then that's because each one of those may have a differential level of, dependency at level two. And then based on that, I could see a way where you could start to build in types of imputation processes for it. It's not going to be easy, though. I think you have to think about it from a perspective of um, I I can almost see like this is one of those things where yeah, some people have built some software for it, some people have built um, some ways to do it, but it's usually a very limited set of examples. And since most of you here are actually everybody here is either in EMS or getting a secondary degree in EMS, so I can tell you this: this is where having the in your toolbox the ability to create your own code to figure out how to do this is really important. Um, you know, it's sort of the push between there'll be a lot of times in science, particularly when we get to sort of new things, where we understand what's wrong with what we're currently doing, but the new things are sort of hard to do with estimation or with implementation, and that's where coding comes in hand, right? And so this is one of those cases. We know the pitfalls of imputation, we know the pitfalls of missing data, but we also have pitfalls with multi-level designs, particularly because we have some variables, particularly random level one, when we have level one predictors, they may be random at level two. And so how do we build a system for it? So I don't have any good answers, but I would say that if you start to think about each of those variables as their own multi-level, like essentially each one needs a multi-level model, but those multi-level models happen simultaneously. There's a method that you can now start to think about ways to start building in random coefficients in the imputation process as well too. So that could be a way, but you would, I mean, to do that, I don't think I'm not familiar with the package that does it. That doesn't mean there's not one that does, but you may have to do it yourself. Experimental. Does that help? Yeah. Mhm. Mhm. Well, the hard part about model fit in model-based imputation is that the model that you're using to impute will have a bias toward fitting better. And right, if you can think about it, if you think about a data set where you have 50% missing observations, just some extreme number, right? And you impute most of them, but they are imputed based on a way that fits the model. You're almost always going to see really good model fit at the end, right? So when it comes to model comparisons, now you have a bigger problem. If you're talking about a model comparison, if they're nested models, if you choose the alternative model, the one that has more parameters to impute with, you can imagine what would happen, right? Depending on how much data are missing, the bias would be to prefer the more complex model. If you choose the simpler model to impute with, the bias will be to choose the simpler model. So where do you end up landing? I don't know the answer to that, right? That's why model-based imputation, I haven't really focused a whole lot on this class because the times I've done it, it almost felt like a little bit like cheating. Like I'm sort of self-confirming what's going on in the process itself. So does that help answer? I don't know if that's a great answer, but Mhm. And of course, all this is dependent on how much data you have to impute. If you only have 2% missing, you can imagine that there probably won't be a big impact of the missing data. But if you have a lot of missing data, that's where it becomes hard. Good questions. Anybody else? Silence. All right, I like silence. So today, actually, there's final in 2 weeks. I gave you a rubric. If you haven't signed up yet, I think everybody in here signed up. If you haven't, just put your name down on the list. You can check the announcement and icon for it. I was thinking about providing a list of questions I might ask you. I might do that next week. All right. I actually created a list of questions first, and I started to refer to them in my final document, and I was like, oh, I probably shouldn't have done that. So I think I'll share those with you, but I'll share those with you probably next week. Let's get homework 5 done and then focus on it. These are questions that if you've been watching the class, if you've been paying attention, these are not going to be hard questions, and it's just a chat. I'm trying to give it least amount of worry in your mind. Okay? I mean, some of you have done this with me before, right? How was it? Did I scare you? Was I fair? I tried to be professional. I know, look, as I get older, I never thought this would happen to me. I realize, and this is what people tell me, I can be really intimidating, and I don't want to be, right? I respect each and every one of you. You have a right to learn as a student, and I want to teach you. That's my job. And I put the final in here in part because I found that with it there's a little bit of just a little, hopefully a little bit of pressure to try to remember to study things one last time before the semester's over, trying to achieve an educational goal. The alternative to that is I've also been in classes where, thanks to ChatGPT, you can go through a class and get an A and not really understand it. So this is a way to sort of hold you honest a little bit as well, too. Not that I don't think most of you use ChatGPT. That's not what I'm accusing you of, but it's more of that's the structure of where I'm going. But if you are concerned, I'm happy to try to even listen to your concerns. I'd love to hear it. You're welcome to talk to me. Send me an email. We can find a time to chat. My goal is just a small 10-minute conversation. I will ask you one, maybe 2 questions, and I'll provide that list of questions next week. Okay? Okay. But if you start reading a script on those questions, I'm going to be unhappy. I want you to use those to study, but leave the mind open. All right? All right. But so here's the funny thing: if you make a script for those, that's studying, so I won't be all that unhappy. But if ChatGPT makes that script for you, ah, just kidding. Yeah, it's up to you to learn the material. I know that, and I know that you're working hard. I do. Okay, so today it's a treat. We get two, not one, but 2 chapter lessons. And I didn't make any examples out of this. I'm just using the book for it, mainly because I wanted to get through these 2 chapters, but I also wanted to spend time next week on psychometric missing data. So next week, we're going to talk about the most important part of psychometrics, which is the score, which is always missing. So that's where next week's lecture is. I'll also provide a few references next week if you'd like to read them about other issues in missing data in psychometrics, particularly when it comes to computerized adaptive assessments and otherwise. Okay? Okay, any other questions before we jump in? All right, onward. Let's talk about multi-level missing data. Can you see that okay? Maybe I should just click the link on the website real quick. I don't have a lot to switch between on this lecture, so let me do this. Now it's time GitHub won't work. You watch. Okay. Does everything have to break all at once? Oh, here we go. All right, there we go. All right, so we're going to talk about chapter 8. I'm going to go section by section. I'm just going to give you my thoughts. I'm going to talk about some of the text, give my thoughts on the text, go from there. There's 87 slides, but again, I'm not doing a lot of examples. So this might go fast, it might not. But let's talk about multi-level. Um, how many of you have taken a class from Lisa on longitudinal or clustered multi-level, or from me? So everybody knows what multi-level data are pretty much, right? Why do we got to worry about why do we have to worry about multi-level data? Dependencies, right? Right. So now most of our analyses assume observations are independent. In a multi-level data, you may not meet that assumption, right? So we have students nested in classrooms, et cetera, right? And not only that, um, these multi-level data happen all the time. Dare I say, a test, when you look at each item separately, is a multi-level data set because now you have responses nested in person. Same type of thing. Well, turns out there are people who would consider IRT or factor analysis to be a multi-level model of a type, right? So there's a big comparison between multi-level data and what we do in a lot of measurement processes. And multi-level data cause a ton of problems. Sorry. Does it cause a ton of problems or does it cause a lot of interesting things to think about? The latter. Interesting things to think about. Problems in some sense. If it gives me a problem, like for me to like show you how to do this, it'd be very hard, I think, in the week for this week. But from a thought perspective, they are pretty interesting. And I think multi-level, I wish I would have known, been better prepared for it when I was in grad school. So the fact that you are working hard on it, these are issues that show up quite a bit, right? You can see multi-level models in everything we do. I think of it, you can make a case for, when I was real young, multi-level certainly was around, but we would call them mixed models and so forth. The Radenbush and Brick book, the second edition Radenbush and Brick book, the Brick and Radenbush book, which the first edition really took mixed models and put that into a didactic, like a real good teaching framework, what we call multi-level now. And you have these, like the HLM program came out of it and so forth. I feel like those were great, but back when I was in school, we would call it repeated measures data, which were also problematic, right? So all of that matters. So um, there are all sorts of sources up here. Take a look at, you've probably seen the Hoffman book. There's other ones as well too, but um, these are classic books on multi-level if you want to know more about it. But missing data in multi-level models is complicated because think about what we've been doing. If we're filling in not y, like filling in our outcome, we realize we can do that, right? That's always all the right hand side of an equation in a multi-level model, all the predictors, the random effects, will work to fill in y. Maybe with an example, maybe that's an example of model-based imputation there because we don't necessarily have y, or better yet, not fill in y, but allow it to be missing at random. It's when we have a multi-level predictor x that's a problem, right? And now we have predictors at multiple levels, right? We have predictors that are level one. All right, let's imagine we have, Vladimir, what's the context? What are you using random slopes for? Can I use your context and data? Can you remind me of it or just, okay, so you have an outcome of math scores, you have students nested in schools, and you wanted to see if the gender gap of math scores, how it differed across schools. Okay, okay, so in that case, the gender gap itself, or you have one outcome, which is math score, and you have, let's imagine, then you have a predictor, which is the gender of the person taking the test, right? And that person, the score is a level one variable, and the person is a level one variable. You have persons nested in schools. So I'm guessing then you go and look and say, oh, does my level one variable vary across level two units, right? And so we probably are making sure that you put in maybe a school mean for proportion of students who might be a given gender, so that you don't have what some would call conflated effects in the fixed effect side, where level two and level one get mixed together. So you disentangle those, but level one now is also random, right? So the effect of gender is random at level one, right? Okay. So now, if you have missing data on gender, right? What do you do? How do you how do you do that? Because, and here's the funny part of it, do you have variation? Are some schools that you work with, what's the range of school mean for, let's say, let's just imagine, let's just use binary sex, men, women. Um, what's your proportion female in school? What's the range of proportion for school? So quite a bit of variability. So all schools aren't created equally when it comes to their composition of students. So think about what would happen then if you ignored the multi-level part, but you filled in gender as a predictor, right? We could do chained equations. We have math score and we have gender, right? And we go and we say, oh, well, math score, let's imagine we're not going to fill that in. Let's just predict, let's do the opposite. Gender predicted by math score. If there is a dependency on students, there'll be some schools. So you're filling in these data for students who give you a score in math, but not in their gender. So some schools, the missing data will come from a 20% female population, and some schools, the data will come from an 80% female population. But if you use our multiple imputation methods up to this point, does it concern itself with school? It does not. You actually have to use that as another predictor. So you can think about this as a way of looking at the multi-level missing data. And then on top of that, that's only filling in gender. That's filling in gender agnostic to any other variable in the model itself. But there may be differences. Do you find that you have a random slope across schools for the effect of gender on math score or the gender gap? Yeah. Yeah. So yeah. So what I'm trying to say is just filling in the data by itself, understanding multi-level premises aren't also enough because the relationship between your level one data, your level two data, and your outcome is still present. And if you fill in only ignoring your outcome, now you're going to fill in a bunch of data that are not related to math score. And what's your result going to look like? It's going to say there's a no effect, right? So can you see what I'm trying to talk about with the problem with missing data in multi-level? Like it's not as easy as having one outcome, right? It's now, or better yet, one level of nesting. It becomes ridiculously difficult. And I don't know that I have, or that the methods that we have right now are what they will be in 10 years, right? So that's just what we're thinking about. Okay, so um, the chapter focus, as you saw, was Bayesian model-based imputation, and then joint model, fully conditional specification with mice or maximum likelihood. But the core idea is that this often involves MCMC estimating factored regressions because we can then disentangle each component um, and creating distributions for those missing values. Right? And so what we really want to do is create imputations where the predictions are from a multi-level model itself. So the noise in a multi-level would be noise, in that case, would be used in the prediction itself. And as you know, in multi-level models, actually, I'll have a slide on that in just a minute. Let's talk about this real quick. Um, on the book's website, I understand there's an educational experiment data. There are about 34 students nested within, per school, nested in 29 schools. And schools were randomly assigned to experimental or comparison conditions. This sounds very much like a setup, almost like your study. It's just instead of randomly, you didn't have random assignment of gender to individuals. Although I did once see a study where they tried to do that. I kid you not. Like in the early days of technology, someone was able to take a video of a person speaking and get their face shape and their tone and change the person's appearance from male to and voice from male to female. And so they tried to randomly assign gender. I thought that was or sex. I thought that was an interesting concept. I don't know how well it worked, but anyway. Um, I'm assuming you don't have that level of technology in all of your schools in Chile, so it's okay. Here, a very similar setup of the design. And here, what we're trying to do is look at end-of-year problem-solving assessments for scores between 37 and 65. These are latent variable scores. Ironically, next week we're going to talk about how actually those are missing too, right? So this week, ignore what I'm going to talk about next week, because the missing data, what happens with an IRT score, does that have perfect reliability? It does not. So now we have missing data issues as well with it. Right? The IRT score itself usually is a most likely or empirical Bayes mode estimate of or mean estimate of ability. All right. So the key feature in multi-level models is that variation and covariation exist at both levels, right? Student scores vary within schools, and school average scores vary between schools, right? So that's the key. We can actually quantify this since everybody nodded that they've been through the multi-level car wash at some point. Call it a car wash. Is that better? No? You frowned. I'll try something better. The multi-level experience. Is that better? Lisa's not a car wash. She's more of a, or whomever you took it from. I'm assuming not a car wash. You have to experience it, right? All right. I'll try. I'm trying for humor. I should quit trying. But as you know, we can quantify the proportion of variance, total variance that's at level, at each level, right? The interclass correlation coefficient. So for instance, an ICC in a two-level model, if it's 0.26, it means that about 26% of variance is between schools. This is also, right, our dependency, an estimate of dependency, right? So that means that observations from the same school are not necessarily independent observations. And this is the thing that I think I mentioned a few weeks ago in when I was looking at Levon output, where I said if the degrees of freedom, the only other times I saw degrees of freedom that were not integers were in a multi-level context or a mixed model context. And that's due to this dependency, right? If the correlation of observations within school is 0.26, and you have 100 students in that school, you don't have 100 unique students. You have something less than that, right? And that's the quantification of effective sample size, right? Design effect and then effective sample size. That's sort of what you have to think about. And that is, if you generate data that ignore this, that new data you're generating is likely to be independent of this, right? And that will no longer be the right ICC. So now you're generating data that are wishful thinking, most likely, right? Thinking that multi-level designs are a problem, uncorrelated data would be wishful thinking. Anyway, all right. The other problem is that's just for the scores themselves, right? Predictors, level one predictors, can also have between and within group variation. And always bothered me about the multi-level models is that we'd be like, hey, let's take, in this case, a school mean for our predictor and then center it, right? Or better yet, let's estimate a school mean and use that in our model, like either through centering or as a predictor itself. Okay, let's think about that school mean though. What do you think about that school mean in the context of missing data? If you have a level one predictor and you go and take a school mean from it, right, to center, like use either cluster mean or person means, person or group mean centering, and you enter that in the model because you understand the issues of convergence, but you have missing data on level one. What do you think happens to the school mean then? Is it accurate? Could it be a biased estimate? Right. So now you have a situation where even if you're doing all the things right in multi-level, if you've got missing data for your predictor, and your predictor is also multi-level, which it will be if it's a level one predictor, you've got to worry about it imputing data as well too. That school mean that you're putting in as a predictor is likely to also have problems. So all sorts of stuff. Like I was already bothered by it being a predictor, so, because this is who I am. What would I say if you could predict me? See how many you can predict this. Probably nobody, because my mind is weird, right? I get it. But like if you had perfectly complete data, what do you think I'd say the problem with putting a mean in as a predictor is? Yeah, you have complete level one data, and you have a model where, let me see if I can, I don't think it's not anywhere close to my slides, but your model is basically you have an outcome Y, a level one predictor X, and then you take the mean for each level two unit of X and put that in the model as well. Yeah, the mean's a parameter. It has error to it. and we put a linear model together, one of our assumptions is that every single variable in our model is measured precisely, 100%. Now, the mean, we know what the standard error of the mean happens to be, but that's still there. And so this is where one of the counters to this was where, again, the multi-level SEM or the multivariate multi-level models will put the mean in as a parameter where it's being estimated. So you can think of, it's easier to think about it in a Markov chain. In a Markov chain, you have values of the mean at every step, right? So each step of the Markov chain, you just replace the mean with its current value that you've estimated, right? That seems pretty straightforward. But you can see now we've got a compounding of problems in multi-level models. Well, number one, you're doing a good job by putting the mean in there because you know convergence is a problem. But the means are usually fairly well behaved. I guess you could probably create data that has some extreme skew where the mean may not work very well. But that mean itself is likely to bias your standard errors because you're thinking it's perfectly measured when it really has some type of error to it. But then on top of that, now if you have missing data, it may not be perfectly measured, and it's likely to bias your other parameter effects as well too, because the mean itself is probably a bias to it. The point estimate's a bias. You get what I'm saying? Yeah. Yes. Um, so the clusters themselves, you're saying you're generalizing across cluster to the bigger population where the clusters are from. The cluster means are also like thought of that way too, so that the cluster means are representative of the cluster means of all the ones in general. Although we don't, unless you get into the stuff that Lisa's in now with her research, where it's conflated or smushed random effects for random slopes, right? The smush level one random effects, and where she has to put in this weird mean as a variance parameter at level two. I don't think we actually have a model that recognizes it that way, right? The variance component itself is really describing how much variation there is across clusters in that quantity, and we won't have a variance component of the level two mean usually, right? It's only under narrow circumstances or when we may have a level three that we could do that. Does that make sense? Yeah. Okay. Right. We have to assume it, but we're not quantifying it in the same way that we do like a level one variable, right? Because the level one variable, if we assume it, basically the random slope variance talks about our estimate of how variable the slope is in a larger population, right? That's what we generalize. There's no similar random variance estimate for the cluster mean, is what I'm saying. And because of that, we have to sort of assume it in the model, but we're not actually implementing it in the model, usually because our design does not allow us to estimate it. But we just have to make that assumption as we go forward, though. Does that make sense? Excellent. This is a topic where we're getting into the philosophical difference between fixed and random effects. And let me tell you, I could spend hours drinking beers talking about this. And Lisa won't talk to me. So if you want to open that door, not with the beer, maybe, but the whole the philosophical conversation is an interesting thing. Like the difference between a multi-level, like if you have a simple like a regular one-way ANOVA and you have 20 groups, right? Do you treat that as fixed effect where each group gets its own kind of coefficient? Or do you treat that as a random effect where you're not really looking at the coefficients, you're looking at the variance across groups, right? One is usually prescribed when we say we have meaningful differences between our groups. Like my example is always, Lisa always likes to talk about my sports data. I used to model sports data when I had a time, and well, I have equally no life now. I just have fewer hours in my day, I feel like. Um, I would want to know the effect specific to a certain sports team if I was going to predict its outcome of an upcoming match or game, right? Whereas alternatively, if I don't really care about which 20 of those groups are different from each other, but I want to talk about variation overall of all the groups. That's the sample of the larger population, right? So these are ways to it. And there are equivalence classes between the types of models for it in certain ways, not all the ways. And not only that, the empirical Bayes estimates for the groups, if you actually go and actually try to provide the estimate of the random intercept or the random components for each group, they will converge to the fixed effects under certain conditions with large enough within cluster samples and so forth, right? But so anyway, too much information. It's kind of fun though. All right, let's start with our regression model here, where we have a coefficient. The intercept itself is allowed to vary randomly across different groups. So this is very amenable. The random intercept models are very amenable to having missing data methods with agnostic imputation and maximum likelihood. Here, ML stands for maximum likelihood. It could stand for multi-level. We could call it machine learning. ML seems to be the word, the letter combination that always shows up together these days. Maximum likelihood for that. So here are our predictors. Maybe at level 1, we have standardized math scores, and at level 2, we have teaching experience. And oh, and by the way, I have not changed what's in the chapter to show you this because I want to go and make the point that there's something else wrong with this as well, right? So here we have an outcome Y. I'm not sure what this outcome happens to be at the moment, but now Y is being predicted by our standardized math score for a student, perhaps, right? This is our level 1 model, right? The intercept varies across schools in this case, but the slope of math does not. And then we have an error term that is assumed to follow a normal distribution with some residual variance sigma squared error. We good? I bet you're going to see what's wrong with this soon, aren't you? All right, here's level 2. Our random intercept shows up at level 2. We have some overall, this is not good notation. I'd like Lisa's gammas here, but I'm using book notation, right? Beta 0 is our overall level 2 grand mean intercept average. Sorry, beta 0. Beta 2 is the effect of the level 2 predictor on the intercept itself. And B0J is a random effect for school. Now, if you follow out this example with standardized math scores and teaching experience, there's a big problem in this. If X here is teaching experience and X here is standardized math scores for school, what are we missing? Not quite. Not quite. Yeah. So the beta 1, because beta 1 has a level 1 variable predicting it. But at level 2, if x2 is not that mean of level, then the slope for beta 1 is conflated. It is not just within level, it is also between level. It is a combination of both. I made that point because I made these slides and I showed them to Lisa. So how many of you have Lisa Hoffman right now in your life in your semester? Anybody? You see her tomorrow? Will you please show her these slides, just a couple of them, and see what she does? Huh? I mean, can you? I mean, this is an example of, so the one thing that Lisa insists upon in multi-level seems to be not insisted upon by otherwise well-knowing people. Like Craig has written papers on conflation in multi-level. You read book chapter on multi-level, well, it's not in there. Maybe that's to make it simple. But I will say in my notation, because I had X2 as a level 2 predictor, let's pretend that's the mean of the math score and just forget the other one. All right? Can we do that? That way I can go home and have a good conscience. How many of you have done a lot of multi-level analyses before? Yeah? When you put the mean in at level 2, how often is that a significant predictor? Almost always, I feel like, right? And I think that's the interesting part about it, right? When you do multi-level, if you just learned it, if people just thought about it as everything's multi-level and multi-level, right? Then it works a little bit differently. Meaning the predictors are in addition to the outcome. But anyway. All right. So we combine these into a single equation. Sometimes we call this the composite equation right here. All right. And again, let's just pretend this x2 variable is the mean of x1. Can we just pretend that, make it feel good? Okay. So now we know with this combined model, though, we do have a sense for with the distribution of y, right? It's basically the expected value, which is this thing right here, plus error. And this is another note that is a little bit interesting, um, depending on who you get your multi-level from, right? Because in Lisa's world, the model for the means is your fixed effects only. But in the multi-level world, in the part, there's parts of multi-level that get into where you actually do need your random coefficient to provide a predicted value of what a value should be, right? So think of it this way. If we didn't include the school effect, the school random intercept, and we imputed, and we were to go and impute data right here without that term, we would lose the dependency in the data, right? Because that term centers a person's observation around their school mean. And yet, like if you, I don't think, at least it hasn't taught you multi-level in SAS in a while, but if you do use proc mixed, they have output for different types of predictions. One is fixed effects only, and one is fixed and random effects, right? And the fixed and random effects, that thing, that school mean, makes the prediction look good. The R squared for the fixed and random effects together is really high. So much so that people are like, we shouldn't use that. But if you're filling in data or you're otherwise looking at the model-based imputation from it, it is important to include it as well. So this is an odd part of it. I will tell you about a notoriously hostile, not hostile, one of those nice academic exchanges where you can passionately argue your points, but not yell. I mean, by yelling, but not being mad with each other. I remember that was like 2009 or something with Lisa. I was like, no, why don't you use that to predict? Because that's cheating. But in some cases, you need it, right? So it's like um, different places have different ideas from it as well. Yeah. Mhm. This right here. Yep. The error term. Ah, great question. And actually, as I'm reading this here, um, the reality of it is we're not including this in part because for any individual it's zero, whereas the expected value for this term for any school across all schools is zero. But for an individual within a school, it's not zero, right? And so in that case, at least that's my having not taught multi-level in a few years, that's how I'm going to describe it. It may not be the most accurate way of doing it. I have low confidence in my assessment, but that's how I'd like to say. Does that sound okay to you? Okay. Can I be, I get, sorry, I've taught multi-level from the psychometric point of view, but not from this point of view. All right. So from this, though, we do have a joint distribution where we can talk about, we could actually figure out what joint distributions happen to be for x, y, x1, and x2. So we could do the factored regression itself. Um, Sequential factoring, we could effectively take the joint distribution of y, x1, and x2. So remember, y is your outcome, x1 is the level 1 predictor, and x2 is the level 2 predictor. Um, we've done this all year long. You had to do it for the Bayes homework as well. Why, if we cannot, we want to use the joint distribution for imputation. In fact, we would love to use it even larger than joint distribution with auxiliary variables for imputation or for estimation. In fact, a regression is no different. But often we can't access the joint distribution, so we break it into a factorization using mathematical statistics. So we're looking at the distribution of y conditional on x1 and x2, the distribution of x1 conditional on x2, and then the distribution of x2 marginally. Seem reasonable, right? So the lower order variables are conditioning on higher level variables. That is an important ordering in the multi-level framework if you're trying to do fractured regression with it. Mainly because philosophically, can you easily make a model where the level 2 outcome is predicted by a level 1 outcome? Right? It just doesn't, it's like a conceptual issue, right? Like the fact that somebody is good in math, does that predict how well the whole school is at math? Not necessarily, right? But the other way around is the fact that the whole school is good at math may influence someone else to be good at math. And that's one of the weird parts of multi-level. It's not always exchangeable in terms of the ordering of variables. So what we can do with this is we can come up with a bunch of models for this. So like, for instance, a level 1 predictor model. This is literally taking x1 and doing multi-level on it. And this is how I started the class talking about. For multi-level methods, you have to think of this case where the level 1 variables are multi-level models too. So some of you, for instance, are generating data for your homework 5 that are multi-level. That's the part that has to happen, right? That's how you generate the data for multi-level as well too. So this is a random intercept model for x1. It's being predicted by x2. And we have some type of residual variable as well too. But that right there is the distribution of x conditional on x2. So you can think about it an approach where we can have the distribution of y conditional on x1 and x2. That was our original composite equation here. And then we have the distribution of x1 conditional on x2. And then finally, if x2 is a level 2 variable, it has effectively an empty model, just a regular simple linear regression with an intercept for it to tell you what the mean of it is. So you can put all these three things together with a random intercept and come up with a factored regression that does the job. Any questions on any of that? No. And so here, we could also do this from a partially factored specification. And I think in some of our cases, we may have done this in the examples this year. I didn't realize that there was a different label for it. So basically, this joint distribution is equivalently equal to the distribution of y conditional on x1 and x2 times the multivariate distribution of x1 and x2, right? They're equivalent. So in that case, it's basically a multivariate normal distribution where there's two parts to it for this f of x1 and x2. I'll just say this and we'll take our break. The x1 part splits it into a series of components, the grand mean, the between cluster deviation, the within cluster deviation, and then there's a within cluster model for x1. And then we build, once we have this mean itself, this overall mean for each observation from x1, it's paired with x2 to produce this bivariate distribution. Now, this is under the consideration that this model would be where x1 is a different variable than x2, right? Where x2 is not the mean, the cluster mean of x2, sorry, of x1, right? But again, it's specifying this in a sequential order to allow you to build out the analysis as it works. All right, I'm going to stop right there. Let's take a 10-minute break and come back, and we'll do some more exciting multi-level thoughts with this. All right, thank you. Let's go again. All right, so we talked about partially factored. Let's get into the distribution of the missing outcome for y. The posterior predictor value for this is basically it's defined by the full model. That's where I flipped back a few slides and said, here's the distribution of y given x1, x2. For imputation, you can draw a random value from this normal distribution, right, where the mean depends on the specific cluster J's intercept, and the variance is the within variance cluster residual variance. And so again, this is the key feature here, where if you don't impute with the specific random intercept with y, there's nothing to anchor that score that you're imputing to the cluster that the person may have come from, right? Or similarly, if this is a longitudinal, if you don't impute the time, if you don't impute the random intercept for person in that case, then there's nothing to tie that observation to the person's data itself. That cluster effect, that random coefficient, is really the glue that puts everything in the same scale on the same focus, right? That's the key thing. The distribution of missing values of x. This is the idea when this is the part where we're getting into in the middle chapters of the book. talking about partially specifying and where distributions are proportional to, but basically the idea is this, that distribution of x given y and x2 is actually proportional to the distribution of y given x1 and x2 times the distribution of x1 given x2, right? And so there's ways that you can derive mathematically what this ends up being looking like. So if you're in that spot where you have to really work to derive this, this might be a guide. I've always found this to be really somewhat difficult to do. This takes a lot of effort. Usually there are some people who are really good at this. I'm not one of them. And so um, finding someone else's work, if you're in a spot where you want to try to use this approach, my advice would be to find recent references where people have done this that are in reputable journals where you'd think the peer review process would make sure the math is right. Right? Or maybe just ask ChatGPT. Have you tried MathStat with ChatGPT? Has anyone done that? I have. I had a for our DCMify project. I wanted to build that MCMC algorithm, and I wanted to sample with the transformation. And I just thought I sort of worked out what I thought it was at, and I thought I'll check my work, and I was like, nope, 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 nope. So found that to be really interesting. Not great at MathStat. Who would have thought? But that being said, all right. So the distribution of the missing values for the level 2 predictor x2, it still has that same partially factored specification where its distribution conditional on y and x1 is proportional to the distribution of y conditional on x1, x2 times the distribution of x2 times x1. And again, this is those component parts are part of it. I don't know if you're ever going to, sample from this directly. Even the book says use often requires sampling methods like Metropolis Hastings. When you hear Metropolis Hastings, what's one acronym that gets in your head? Initials. Metropolis Hastings is a MCMC method, right? So that's where that tends to show up. So we can talk a little bit about an MCMC algorithm. How to do this. The posterior distribution is this complex function describing the joint probability of parameters, random effects, latent means, and missing values in the observed data. And the core logic in MCMC for multi-level extends from regular Bayesian MCMC. The idea being that you estimate one unknown quantity at a time and then condition on the current values and all the other quantities. And this is what we talked about with the Markov chain. I won't say, technically speaking, one unknown quantity could be one set of unknown quantities. In the algorithm building business, sometimes we call that blocking. Like we have a block of parameters we're sampling at once, particularly if we have a joint distribution for them. It's an efficiency thing, right? If you separate where you do a sampling process for every single parameter in a multi-level model, included in that are all the random coefficients. So you're going to be likely to sample random intercepts, random slopes, and et cetera. So you quickly run into a spot where you have tons of parameters, right? So there may be a chance where the algorithm itself is not just exactly one at a time. It might be one set of parameters at a time. You can find full conditional distributions for most of this under multi-level models where outcomes are conditionally normal and random effects are normal. Once you move away from those specifications, the full conditionals start to become difficult, just like we saw with the full idea of conditional distributions in Bayes sometimes, right? In regular univariate Bayes, depending on your prior distribution that you use, you may not have a full conditional distribution that you can derive. Right? If you do, you can sample using Gibbs. If you don't, it's a problem. Yeah, question. Yeah, I don't know what the lingo in MSIM is or whatever, multi-level SEM. Um, but yeah, those would be the unestimated means. I really hate the word latent for everything. It's a parameter, right? So the latent means in this case would be the cluster mean, right? Latent. Yes, latent, I guess, technically speaking. But again, in this book alone, we've had actual latent variables, although there haven't been many of those. We had underlying continuous things that were called latent when we talked about the Albert and Shib method for doing MCMC. And now we're calling the means a parameter latent as well. So you'll see in the SEM world, this is part of where I don't identify with the SEM group as much. Everything that you haven't observed is latent, even if it's a parameter that you're trying to estimate, which is kind of an odd way of putting it, but that's the hammer. You know, the saying, if all one has is the hammer, all one sees is nails. The latent hammer is the SEM approach, right? But it's accurate, it's right. It's just somewhat annoying if you learn other parts of statistics with it that you have to keep calling everything the same word. Yeah, that's right. Right. So the cluster mean in this case for MCMC is used in your model, but not by you. So your model treats it as a model parameter. So you can think of an MCMC algorithm where you specify your cluster mean. Basically, you're saying, um, it's almost like a hyperparameter in our case, an empirical base, where you don't plug in the mean of each group. You are estimating it as part of the Markov chain. So that mean is having is sampling from a posterior distribution. So it has variation from step to step. So that outcome model that you build, where the mean is a predictor in it, will have a different value of the mean potentially for each cluster at each iteration. Yes. And you can think of what that does to the variation for the slope that it multiplies. If x keeps changing, that slope will have should have a wider posterior distribution as well too, because x is no longer constant, right? There's variability about it in addition to variability that existed already in the data, right? Yeah, you're welcome. And actually, that's my disconnect between MSEM, multi-level SEM, and Bayes, because I learned Bayes first. In Bayes, it's just a hyperparameter. It's not a latent mean, it's a hyperparameter, right? We got this. We could put that in a model. But again, it's a difference in language, not a difference in notation. It's a difference in only language. But it does matter if you go give a job interview where there's a bunch of multi-level SEM people, they won't like you calling it a hyperparameter. Similarly, if you're in the Bayesian sense and you call it a latent mean, people are like, what are you talking about? Sound good? Sound good. You can see the generic recipe. You'll see this as well. I mean, this is really very generic, but he put it in the book and I thought I'd share it with you. For each iteration in a chain, you start with a set of starting values for all parameters, random effects, and missing values. So you have complete data and completely random guesses as to what the parameter estimate should be. And then for each iteration, you sample each one of those things. Right? You can think of every part of this highlighted in pink here as what's being sampled in the markup chain. So step one, you might get the parameters. Step two, you might get the random effects. Step three, you might get a predictor model parameters. So in this case, the predictor model is the idea of the multivariate multi-level, like I like to talk about, where X also is a multi-level model. So you'll have an outcome for Y, you have an outcome for X, and then you'll have an outcome for each of the level one X's, like model for those, right? Where X, remember in Bayes, how we specified it in JAGs, the variable follows the distribution, right? And in this case, Y, the final outcome, the big model, is the distribution of interest. But to get to that big model, you still build in a distribution for each of the X's as well, too. Right? And do that because that way, that distribution allows you to not only sample the parameters, but also impute the missing values using Gibbs sampling throughout the process as well, too. And this is model-based imputation if you do it this way. How's that sound? Okay. Here's the next. By the way, ironically, this looks like it's a sequential list down here. So long as you allow every parameter to change, have a chance to change its state in any iteration, it doesn't matter what this order is right here, right? So long as that list is comprehensive, that's why I know I put dots and not numbers there. Right? So if you're building your own algorithm, just remember that sometimes it's more convenient to sample one versus the other. So, all right, an example analysis setup. So if we have problem solving skills here, there's a random intercept, there's overall fixed intercept plus a random effect for school, math pretest scores at level one, standardized math scores at level one, free and reduced lunch at level one, um, teaching experience, which is a level two variable, and condition, which is a level two variable. What will Lisa Hoffman have to say about these right here? Is beta 1 a level 1 slope, a level 2 slope, or a blend? It's level, no, it's a blend because there's no mean of pretest in the model itself, right? By the way, you ever go to multi-level, not multi-level, you go, you know how we have our AI overlords taking over the world right now, right? Everybody loves AI. Who doesn't love a good AI talk, machine learning? You ever want to see a field that has not yet discovered multi-level struggle? Go to an AI talk, make it a job talk, even better, and ask the person, are your hypotheses within or between? Right? They will have no idea what you're talking about. But guess what happens if this is like a machine learning process and all of our machine learning coefficients are conflated? Not so great prediction. That happens a lot. So just a heads up, those of you who want an active research area, bring multi-level concepts to machine learning, make the world a better place. Promise. All right. First, you got to convince them that it's a thing, though. I mean, all right. Don't get me wrong. I like machine learning stuff. It's actually kind of cool. We do machine learning in what we do. We just don't call it that. And again, another language difference. Boy, I'm on a roll today. It's just opinion. It's just the opinion hour. I think I've officially reached old age. God, what happened to me? All right. Anyway, once again, why this is conflated is that any level 1 variable is likely to have level 2 variation in it. And the only way that you can disentangle the level 1 effect from the level 2 component is to include, in a crude sense, the mean at pretest at level 2 as a predictor in the model. Without it, this level 1 slope is sort of in between. It doesn't apply to any one person or any one school. It's a blend, right? Same thing with standardized math, and same thing for free and reduced lunch. One thing I'm always amazed with when I teach multi-level or I do multi-level is how a person can come in with 3 variables, and all of a sudden I have 800 parameters in my model. Have you ever been that spot? Because you have to sort of disentangle certain features. I wouldn't say 800, but 3 variables quickly turns into 16, right? When you talk about school level effects, when you talk about cross-level interactions potentially, all of it becomes difficult. All right. I will say that this is a 2-level model. The beta 4 and beta 5, the condition and the teaching experience variable, those are only level 2 slopes, and they are not smushed or conflated. All right, so the goal here is to estimate our treatment effect for beta 5, which actually in this case has no missing data, but controlling for other covariates, right? And I will note, this is my note here. So if you read the book, remember my note. Because guess what happens if you use this as your imputation model, right? You've just imputed conflated slopes, level 1, level 2, smush slopes. There we go. All right, but you don't need to hear that from me. If everybody starts talking about smushing, you're going to run being like, gosh, just make it stop, right? How often does Lisa say smush every class? Let me ask that question. Is it at least once a class in multi-level? At least once? That's good. You want to see, how many of you have her class? Let's make this kind of fun. I'm going to make an estimate here that she's going to not say smushed. I'm going to give you a time point, and I want you to time her, and I want you to record the first observation of the word smushed in her class tomorrow. And I'm going to give you 15 minutes. Oh, never mind. Oh, that'll show up. Then never mind. I can't do that. I can't do that. That's not her teaching. Yeah, that's too bad. That's too bad. No, I actually, that's the good. Actually, I really like her. I'm sort of joking about it. This is not meant to be a put down. It's really a disconnect between when you read other people's multi-level books or you read other things in multi-level, and then you go and see what she does, and you can see the impact of the smushing on the multi-level design. Okay, at the very least, it's different. Let's say that. But it's different in ways where we know that's going to bias results. So it's amazing to me that when you read a multi-level textbook not written by Lisa Hoffman or some other select individuals, it is so hard to not see that in it. You know what I'm saying? It's just interesting. So I'm belaboring a point here, but I'm belaboring that point because when you do impute missing data, you've got to worry about too. Yes. Lisa's? Snyder's, I think Snyder's does have a component on it, yes, but I don't think for, but Lisa's. Yeah, I don't know enough about the rest of the books. So I'm not going to, actually, I will not put any book down without reading it. Let's put it out. So I don't know exactly that. That is a better question for her than me. All right. So here, we can do this factor regression. We could do a product of univariate distributions where the order is incomplete level one, complete level one, incomplete level two, complete level two. And then we use, Craig likes to use the latent response. Again, yeah, there's that latent word again for binary predictors. Remember what that means? That is the drawing a underlying continuous variable from a truncated normal distribution, right? So for observed data, if somebody provides a one for a binary predictor, you draw a truncated normal variable, truncated below at zero, using the expected value of the regression coefficients to be its mean and a value of one to be its variance. It's a probit model in that case, right? Similarly, if the true value were zero, it's truncated above at zero, same mean, one for the variance. And then if it's missing, it's not truncated, right? So it keeps the variable continuous. There's no benefit to doing this statistically, with the exception of if you're building your own MC algorithm, it is actually quite a bit more efficient than sampling from posterior distributions on logistic or other distribution, Bernoulli distributions. It seems to work very well. But again, that is what the book talks about. So here, if we do this partially factored instead, the approach would be a multivariate normal for our predictors themselves. In this case, free and reduced lunch again would be the can't be multivariate normal unless we allow it to be the, again, the underlying continuous, what Craig calls the latent response. Yet again, another instance of latent, right? Okay. All right. So you can see the partial factorization as well there. All right, let's just move ahead. I don't have a great example for it, so I'll just keep going. Um, let's talk about random coefficient models, in this case, random slopes. Right? This is an example from a daily diary study from Health Psych, where there were 132 patients with chronic pain, and they went and had them report about their pain multiple times a day. You've seen this design before, right? So now we have observations nested within person. We have actually observations nested within time versus in person, or person within time, depending on how you think about it. Um, right. So we have daily assessments up to 21 days about mood, sleep, and pain, and then we have level two for being persons. And so our variables are level one are all the daily assessments, and level two are the person level demographics and psych variables like pain acceptance and catastrophizing, which is what I tend to do when I talk about multi-level and smushing. It's a catastrophe. Maybe not in the same sense as pain, but never mind. I'm trying. Um, here, there is the positive affect interclass correlation is 0.63. It's pretty big interclass correlation, but fits with lots of multi-level designs. That's a number that we would normally see, mainly because observations from the same person in very proximal amounts of time tend to be highly correlated, right? So that works. So our random slope model, the concept of this is a multi-level regression where the influence of the slope of one or more level one predictors varies across level two units. So here, daily pain may predict positive affect, daily positive affect, or person average pain and pain acceptance may also predict positive affect. The key is the effect of daily pain on positive affect can differ from person to person. That's the random slope, right? Each person's effect of daily pain may be different, right? For instance, when I broke my wrist, thankfully I wasn't in a lot of pain, but my affect was not positive. I'll put it that way. But many of you might be better suited to such small injuries like I had. But I will say my person level random slope was negative. That's all I have to say. All right. More pain, less positive affect. I don't know about you guys. I don't know of anybody who's just positive though. Does anybody? Never mind. All right. Actually, the slope is a deviation from the overall grand mean. So therefore, mine still would be negative because that's just how it is, right? I get it. All right. So level one model within person looks like this. Oh, look, there's some mean centering going on. It's positive. Now, did we put the mean at level two? Uh, no. Wait, maybe. U1's right here. Maybe. All right. Anyway, so here we have a slope that's random. We have an intercept that's random. And then the level two model here, we have a value for our random intercept that looks at the person-specific deviation of the person mean from the overall mean. So it is at level two. That's good. It's a little bit less conflated. And then we have for the slope itself, no predictors of the slope, but just some random variance. Now, again, this is just meant to give you an example. Most of us will probably have some type of prediction going on for those slopes, right? We want to describe why people vary in their effective, level one or daily pain on daily positive affect, right? So here the key is that we have these two random coefficients, beta 0, beta 1. Those follow a multivariate or bivariate normal distribution. If you're in Lisa's class, this thing is called the G matrix. Seen that before? Borrowed from SAS documentation, which is the greatest documentation in the world, Proc Mixed. Learn mixed models. That's how I did it. Go read Proc Mixed manual. It's actually pretty good, quite effective. Still, all right. Here's our reduced form or the composite model itself. Right, all this part really looks like the overall random intercept, and then the overall random slope is here. Right, but again, now you can see that y. The expected value of y, though, when we talk about the expected value of y, is all of that in the pink on the screen. So we do, when we talk about if we had to do some type of imputation for y, we'd use that whole term, including random intercepts and random slopes. You can think about what would happen if the random slope we didn't include in y, right? It would force everybody to have the same fixed slope, which is a problem. The other problem with this is that Vladimir had asked about when we started class is if this is the second model in your modeling process, right? When you learn in Lisa's class, she usually talks with a random intercept and then a fixed linear slope, then a fixed random slope, and a fixed time fixed quadratic, something like that, where you have this sequence of models, your model building. If you were doing imputation the whole process, you'd want to make sure that sequence is well known until the end and impute with the full model at the end, I think. But is that really appropriate? I don't know. So why I say is that really appropriate is that you're favoring one model. It's model-based imputation. You're favoring one model to build the whole process, right? How do you figure out whether that's appropriate or not? All right. Actually, let me say one last thing about it. There is a group of people who do mixed or multi-level models. You may have heard of them. Maximal models. Have you ever heard of those? Basically, let everything be random. Let it sort it out at the end. When I talk to Lisa about it, I kind of like it. She doesn't, right? So, and why she doesn't like it? Because it's not very parsimonious, but it's also not very pragmatic, right? If you have, let's say, 3 or 4 different level one predictors, now you have a G matrix that's 4 by 4. And I don't know about you, but if you've ever tried to estimate one of those things, it might be kind of hard depending on your data, right? That's where I go Bayes. It's okay. But if you can get over the estimation challenge, when someone said it didn't work, I'm like, haha, that's where I like to live, where it doesn't work. If you get over that estimation challenge, I like the maximal model approach because it does fit with missing data overall. Let everything be random, right? And if it's not truly random in your data and you can estimate it, what you should see is that variance of the slope should be so close to zero that even including it in an imputation or a multi-level perspective will not change things. It'll basically go away in general. But again, if you're doing this step by step, picking one of the models to impute with is going to be hard because they're all going to look like it. All right. There could also be nonlinearity in all your data, as you noticed. I haven't done anything with random slopes. So if you remember the part about nonlinearity back in when we built up the models before. We have the just another variable approach where we make a product of variables and allow it to do, which I know we've talked about, and for with respect to your homework. And sometimes you have to do that approach, right? But basically, all of the methods that you saw before still apply, but the application is now a little bit more complicated because nonlinearity. What's nonlinear? Do you need a nonlinear effect of x2, of x1, right? And remember, nonlinearity might be adding a quadratic coefficient for this predictor to your model, right? In which case, nonlinearity wouldn't be the worst thing in the world. You impute x2 and you find a way to square it, but that doesn't always fit with imputation software, like mice, for instance, right? So um, again, we can do the factor regression specification here. And here we look at the distribution of y given x1 and x2 times the distribution of x1 and x2. So here x1 and x2 were the parts that had random coefficients. And why this is a little bit more straightforward is when x1 and x2 have random coefficients together, their joint model will look a certain way that allow it to be used in factorization. It's harder to factorize in between. And again, the missing values of y. We can go through all this as well too. There can also be, sorry, I'm just kind of skipping ahead here. This is sort of a sampling of the multi-level, but I'm going to go a little bit quicker so I can get to not at random for the next hour. All right. Let's see what we, if you have questions though, slow me down. All right. What happens if you have heteroscedasticity in X1 imputations? That's a problem, but you kind of do, right? So the variance term for X1 missing has a component in there as well, right? And so the variance of this imputed distribution depends on the person's specific random slope squared. So that means that imputations for X1 will have different variances for different people. This is the nature of heteroscedastic. But the problem, and this is where the random slopes become difficult to really work with, is if you need this term in it, how do you know what that term is a priori? Right? How do you figure out a person's random slope? You estimate a model. But if you estimate that model when that person's random have some of the x's missing, that random slope may be biased. So how do you disentangle the biased random slope from the model to then go and use it in the model to be able to keep forward? This is the black hole of, like, you can't get out of missing data wise, right? I still look at this as a quintessential challenge for multi-level. It's the same thing with in multi-level where you get to random slopes and you're trying to think about, like, does your model fit the data very well? Or you get into certain aspects of it and you have no alternative distribution that you can think of because everything would have to be random at that case. Looks very weird, right? So there's parts of multi-level that take you out of a context too far away from where most of our stat models live. But I don't know about you. I think this is pretty accurate, right? This is a simple random slope, one of them. How many of you will have a random slope in any of your multi-level analyses? Most of you will, right? And if you have missing data, there's the problem you face. So, all right. Multi-level interaction effects are going to work very similarly again. This is the example he gives from employee empowerment study where you have 630 employees from 105 work groups or teams with about 6 per team. And so level 1 is employees are nested within those work groups or teams. Your outcome variable is empowerment. That sounds good. I like empowerment. The other variables are leader member exchange, LMX. That makes it sound really nice. The gender, in this case, male, team cohesion, and team leadership climate. Here you might have a cross-level interaction, right? So you might have the influence, the slope of a level 1 predictor on Y being moderated by a level 2 predictor, right? So the example here, if we have, what was it, leader member exchange, which is a measure of within team relationship quality, this team leadership climate moderate the impact of leader membership exchange on employee empowerment. It's a mouthful to say, but it seems plausible, right? In some environment, in some climate, in some type of team leadership climate, um, leader member exchange may be good, and some may it not be, right? But you can see what's going to happen. We have this product term right here, cross-level interaction. If we have missing data on X1 and on X4, what do we do? Right. Again, we can use model-based imputation, something that we see right here. And when I look at a model like this, if I'm going to use quote unquote model-based imputation, the thing I go to first is just build this model in JAGs, right? Remember when we use JAGs in our class, where JAGs suffered was auxiliary variables. Remember that? We don't have auxiliary variables here. This is pretty straightforward model-based imputation. And what that means is if we put a model in for X1 and we have a model for X4, then JAGS is filling in the missing data on each of those variables, right? And so that means that every time you fill in the data in another step in JAGS, you have complete data for this part, complete data for that part, and you can put the product in on a single line because JAGS doesn't make you form the product variable before you bring your data into it. You can do it in the process of the sampling itself. So when I say this, when I'm talking about all this, I'm envisioning all of this being implemented probably in JAGS or some other Bayesian software. I picked JAGS because if you have missing data on, let's say, X star 2, technically, yes, you can use stan to do the continuous variable approach, but I'm not sure. I haven't ever tried implementing it in stan. I'm not sure if it would actually work all that well. But JAGS will handle discrete variables that may have missing data as well, too. Right? How are we doing? I feel like I'm just rambling. No? Does it make sense? So if you're going to do this, my first thought would be, if you come to me and say, how do I do this with my data? Like, start getting ready to put it in JAGS, right? Build it all in JAGS. Similarly, you can have the factored regression specification here. Remember, the interesting thing about factored regression is when you have a product, in this case, X1 times X4, that interaction, the distribution of the interaction is basically resolved by looking at each of the components of the interaction, so long as they're in a distribution too, right? So long as that X1 and X4 are in the joint distribution to factor this, it should work fine. The hard part with that, again, is, and this is a challenge I recognize when it comes to writing this book, the interplay between theory and software, right? You were mentioning how you had to use factored regression because, or not factored, just another variable because multiple imputation in mice will not let you go and form a product after imputation. And so you need that product there. So you made it just another variable and imputed just another variable with it, right? That's a software problem, not a theory problem, right? And I can only imagine how hard this version of the book was to write for that reason too, because you've got all these approaches to missing data that exist in the world, in the literature, in the universe, the known universe. Let's just say that. That planet that we saw that had some type of biological gas marker on it, maybe they're doing multi-level under their methane oceans. I don't know. But in our known universe, um, there's no easy way to implement all of it in all software all the time. So, and then we get the distribution of missing values, similar to the random coefficient model here. The variance depends on the random slope in the interaction term. So it is very difficult, and I like this. Metropolis Hastings is useful. Yeah, go use JAX. All right. Can you guess what I'm going to say about three-level models? How many of you have three-level models? Nobody else? I'll try. Same thing. It's just more of it, right? Because now if you have a variable measured at level 1, it may have level 2 variation, and it may also have level 3 variation, right? And then the variable measured at level 2 may have level 3 variation. So there's a lot more problems to go. This example is from measurement occasions at level 1, students in schools, and the outcome is problem solving, right? So we have this sequential phase data where the final wave had about 20% missing. And of course, there was planned missingness in the control group. Planned missingness is a design where you can not have to give everybody, sample everybody all the time. I will say about planned missingness designs, I think they're a lot harder to design than they sound, because whenever you say, I'm not going to collect these data on these people at this time, you made an analysis later that needs that data, and then you're kind of stuck, right? So, so here, an example is a longitudinal growth model. Actually, this is a different example where the month predictor is level one, which month the data came from, and month, because it's constant, and we don't have everybody applies the same month. Um, there's no variation at level two, level three. It's one of those time variables that seem to not necessarily need a random component to it at level whatever here. So here we have a trajectory. We have a random intercept for person within, sorry, time within person within school. Actually, time within person in this case. So this is the expected score for student I at month 0. And then this is the linear rate of change per month for student I. Both of those are random as well. So we have between student model itself, where we take the standardized math score for a student at the end of the year, or the free and reduced lunch status of a student, mean centered in each of those cases, and put those in to predict the random intercept. Here, the random slope again is allowed to not have any predictors. I don't know why you do that. And then the level 3 model takes each of those random coefficients and then conditions that on other features such as teacher or the experimental condition itself. So now, with all of that, we have a huge combined model. Again, don't you love multi-level? We had like month, and what do we have here? We have like 4 or 5 different variables, and they're all in a big composite model. All right. So we have a month by condition by month interactions to see if the effect of this study changes over time. Right. That's sort of key feature. And again, we can use a factored regression where we take a look at the distribution of y conditional on all the x's times the distribution of x's. Yes, I got lazy. I'm sorry. That's my all the x's there. Guess I could have made it a big matrix x. I didn't. We can decompose this as well. Remember, level 1 predictors are decomposed with level 1, level 2, and level 3 components. Right here, we have the level 1 x, grand mean of x, sort of the level 2 deviation from the grand mean, and the level 3 deviation from the level 2, and so on, right? Conceptual itself from that model. And again, for each one of the other predictor models, we can do the same thing, right? We do this factored regression approach depending on how things play out. Okay. So let's talk a little bit about multiple imputation strategies in the next couple minutes. Here, we're going to talk about agnostic versus multi-level based or model-based multiple imputation. In what we've done today, agnostic is the closest when basically the set of models that work the best with agnostic, again, is the random intercept models. Random intercept models are nice because they only have that random component for the intercepted, and the random slopes are assumed constant around people. But here I'm going to ask a philosophical question for you. If the random intercept model is truly only the model that's agnostic, meaning we can go do imputation based on auxiliary variables and other stuff, is it really agnostic? There's a thought question for you. And I say that because isn't random intercept a type of model? Wouldn't that make it model based? To say, oh, you can use agnostic so long as it's this model makes me think, no, actually, it's not agnostic. It's actually slightly more agnostic, but it still has a model base to it, right? Because how often do you know your random intercept model is right? Reviewer 2 is certain it's not right. Let's just put it that way. So I would actually go and say it's not truly the case that we can be fully agnostic when we have to specify the type of random covariance structure, random variance, random effect structure, right? What do you think? Thought provoke. Well, yeah, I don't know. Right, that's what I'm saying. So if you say, "Oh, I'm going to use a random intercept model because I can be more agnostic," but your data don't support a random intercept model, it should be some type of random coefficient. Otherwise, you've just done model-based imputation with a lot of other covariates or auxiliary variables. It's tough, right? So anyway, yeah. Mhm. Yes, absolutely. Same thing. And that's the problem with the multi-level, the imputation in general and multi-level is that there's just no end to the multi-level being present, right? The dependency being present across the data. And that is why I led the class as multi-level problems, or better yet, research designs. This is the problem with it, right? The problem is um, even under what we call agnostic, you have to be a random intercept model, which then takes you out of agnostic, is what I would say. So maybe a semantic argument, but it's not fully semantic. It's not fully agnostic. All right. So there is a caution. We don't want to do single level multiple imputation on multi-level data. I've been talking about it through class. You can see why though, right? If you say that there's no dependency in your data, you've just injected a whole bunch of independent observations into a spot where there are dependent observations. It's going to make it look like you have more power that you have for certain effects. It's going to potentially bias your estimates, right? It's going to be a problem. Um, about that. Yeah. I'm just trying to think about what I want to highlight more on here. So the other part that I'll mention is that when you use maximum likelihood to do multi-level, all this is much harder also, right? Interestingly, though, it is and it isn't. To the extent that you can trick software to do multi-level using maximum likelihood, or in our case, residual maximum likelihood, restrict REML, um, you may be able to do this. What do I mean by that? Did Lisa ever give the lecture where she described a multivariate, multi-level model, but she got it to run using just a regular univariate package? Ever seen that before? She like dummy codes which variable it is and has dummy codes for random effects and so forth. That's an example of model-based imputation from a multivariate, multi-level model. You can do it. You just have to be able to trick your software. Problem is most multi-level software, it's not the SCM framework is built for one outcome. But you can trick that software to do more than one outcome. And that's one way to do it. But that being said, that's a very limited case. And it's hard to think about how to go beyond it. But there's some breadcrumbs to think about. Breadcrumbs? I don't know. There's a line of hints to think to follow if you're going to do that. If you have now, that's when you have missing data in both outcome and predictor. If you have only missing in your outcome, first of all, you're a unicorn because I don't know why that variable got favored to only have missing. Or maybe you're in a really tightly controlled experimental design. Maybe that's it. But missing data for the outcome meets MAR under maximum likelihood as it is. So if the only thing that's missing is Y, you're fine. No big deal. Still, the problem is, I mean, how realistic do you think that is, though? The likelihood that you have a study and you're only missing your outcome of interest. I haven't worked in that scenario, but maybe there are people. I'll leave it to be hopeful that there are individuals in the world that have that. All right. Yeah, but the challenge is the predictors itself, because MLM packages often default to list-wise deletion, and that assumes MCAR, right? So, all right. The multi-level SEM framework is useful in this case, but it still also has lots of problems. Oh, look, best suited for random intercept again. So, those of you with random slopes just don't have missing data. Problem solved. Yeah. So that's my summary. I know we're running out of time right now. I mean, that's basically what this has ended with, right? So it's like just like in the Bayes chapter, which is, oh, you're going to do Bayes and Jags with auxiliary variables? Ah, good luck. Enjoy, right? Here it's you're going to do you're going to have missing data with multi-level and random missing predictors. Under some cases, yes. It's hard to do otherwise. So let's in the moment I have left before we have break, let me just put it this way. If you are trying to publish papers with helping people or your own research on this, you can expect that people will be concerned about missing data, but that you won't have the right answer always, right? But having a strategy for how you imputed or otherwise handled missing data would be important, right? So having a section of your description for your analysis method to describe what you did for missing data. It may not be perfect. I don't know that there is perfect, but including it is likely to be the case to be needed because review audiences are familiar with missing data. They may not be super familiar with missing data under multi-level or your specific model itself, but at least address. I always feel like it's better to address a challenge head on, write about it. It's better to talk about it with authors as well and describe the steps you took. If you make an honest attempt at it, I think that's the best you can do. This is where we're at scientifically right now. Hopefully in a few years it won't be this way. Somebody will have figured out a different way of doing things that will be amazing, or we'll just have Chat GPT impute all of our data. On that note, let's take a 10-minute break and relax a moment. We'll talk about missing not at random when we come back. Okay? Thanks. Start our last hour of the day. My feet are tired today. I feel like sitting down. Must be this conference I went to. So I didn't walk as much this time as I usually do. But still. Okay, so that last lecture ended everything about missing at random processes. The end. You're all experts now, right? The moral of this class is don't have missing data. No, that's okay. Uh, Learn to live that maybe this is an active research area that you can get involved in your data. This is good. Missing not at random has been held out from the whole class to this part. In fact, we sort of decided that, hey, missing completely at random, any analysis like that is just what we call a normal analysis. To try to make sure that we meet missing at random assumptions, we had everything in between up to this point. And now I'm going to mention just briefly about ideas for missing not at random. These are also difficult, right? And the reason for it is missing not at random assumes that some of the missing values contain unique information about why they're missing. Seems plausible, right? I mentioned examples of missing not at random. I mentioned polling error. People who didn't answer the phone or didn't reply to a text message about who they'd want to vote for, in part because of who they wanted to vote for, right? That would be an example of it. Um, I would say, I'm going to summarize this to begin with as more of the wishful thinking. Good luck. But as you can guess, you have to make some assumptions somewhere about that missing process. And it's not always obvious that your assumptions are valid. So I look at this as almost as if saying a couple things. One would be if you have multiple sets of assumptions about what's missing and why it's missing, you may try different models under those assumptions or try to build different approaches to this. It's not even a model, it may be an approach you have to build under those assumptions. Basically, if something's missing, here's why. But there will be multiple reasons, right? I don't know about you all. Actually, I bet you all are more right than I am. But in my many, many years around the sun on this planet, I tell you that I'm wrong like all the time, right? And so if I'm going to be like, hey, I think they're missing because this, you can go ahead and guarantee that that's not going to be right. It may be maybe approximately right. That's the best I can do, right? So what am I saying with that? This is the idea where you might have to do multiple sets of analyses under multiple types of assumptions. Because under those multiple analyses, you may get different results. And then it becomes a question of aggregation. I've seen this before, though. Let me see if I can try something real quick here. Let me give you an example here. You've seen these lines before, right? Now, this is not necessarily missing not at random. There's nothing inherently missing not at random about it not observing atmospheric conditions about it, weather. I guess potentially if the only times that would be the case is if the conditions in the atmosphere are such that we can't measure it. Like if it's too cold or too warm. But I think our technology is such that we probably can. It's just really hard to get this. But what am I saying about multiple models is the following. These multiple models were all initialized with different assumptions about what the current status of the atmospheric environment was, where the center of the circulation of the system is, right? So because of that, you have this. Now let's flip to missing not at random and pretend this was not missing not at random, right? If you go through a process of missing not at random, making assumptions about what it is about missing data that's random or not at random, you would have a similar ensemble, sometimes we call this ensemble model approach to it, right? These are all different outputs of model runs with different assumptions about where things start. In your case, it would be different assumptions about why missing might be. And similar to this, what do we do with this once we get this ensemble, right? The next step then is some type of model averaging, output of a model averaging to determine what's most likely to happen. And you can see that in sort of these cone diagrams, right? This is sort of a model average of where a hurricane might go based on model predictions. In your data, you might have a prediction model for your output based on certain features of missing not at random. And then your challenge is to figure out how extreme those assumptions are for a single snapshot. So that's what I look at for missing not at random. And anytime I can put weather data in class, it makes me feel like I'm doing the wrong career, but I'm too late to change it now. So we'll see. Okay, questions on that so far, what I'm saying? Great. You'll see there's 27 slides in this one, so it's not a long one. It's basically like, yeah, here's a few things, but otherwise, good luck. Right? Isn't there a, like, what are you going to do? All right, the challenge is this. The probability of missing this is related to the unseen score values themselves, and you didn't observe them. Gosh, that's hard. So the problem is that standard analysis assuming missing at random only, which does not assume missingness is related to the score values that you didn't observe, right? That's the big difference between missing at random and missing not at random. If you assume missing at random, but it's truly not missing at random, bias happens. That's always what happens, right? You do something wrong or wrong. You make the wrong assumption, an accurate assumption. And what's going to happen? Your results are not going to be as accurate. They're going to be somewhat biased, right? So the goal is to sort of mitigate non-response bias if you suspect missing not at random. The book describes two major missing not at random frameworks. Selection models, which try to model the probability of missingness as an outcome, and then using a regression equation with missing data indicator as a dependent variable. So now, can we predict what's going to be missing to try to understand why it's missing in the first place? Um, and we can also treat missingness as dependent on the analysis variables that way. The other approach is pattern mixture models. And this is really where, in the early part of class, and one of the first homework assignments, or actually a couple of homework assignments, I asked you to look at the pattern of missing data, right? This is where those patterns become a little bit more meaningful. Missing model data patterns basically miss those data patterns based on missingness itself, and use the missing data indicator as a predictor or moderator itself, right? So basically, what is the reason why someone has this pattern of missing data versus not? And you may also assume different parameters for missing data patterns. So basically, if you look at someone who's only gave you two variables, it may be one type of prediction. If it misses somebody who's given you three, it may be a different type of prediction. Um, so the big thing, as I mentioned previously, is that missing not at random models require strong, often unverifiable assumptions. Nothing like a strong, unverifiable assumption to make you feel like you shouldn't be doing statistics, right? Back in the old days when quantitative researchers and qualitative researchers used to butt heads, which I hope doesn't happen as much anymore. I think all methods of inquiry are important. I just study quant methods. Um, that's almost like you're arguing as to which side your belief is right. I mean, things that you can never. I mean, it's like arguing whether or not Santa Claus would beat the Easter Bunny in a wrestling match. Right. First of all, you have to have a belief in either. Right. And second, like who's going to win that? I mean, like, I don't know. Right. I'm trying to think of like what are other mythical creatures? Uncle Sam or American mythology is going to go in and arm wrestle with some. I'm trying to think of pick your mythology, right? That's what you're talking about here. And ironically, I feel like that's where some of the worst, bloodiest battles are, where you have to argue based on philosophy only because there's no evidence to support one side or the other. It's really difficult, or whatever side it happens to be on. So it's really difficult. What are the assumptions, though? Distributional assumptions for selection models, specifying inestimable parameters for pattern estimate models. So how do you estimate a parameter that's not there? Basically, what's the effect of this slope if nobody gave you that variable in one of the patterns? And really, the problem with this, as I mentioned before, um, you're missing not at random models um, can potentially increase bias much more so compared to missing at random analyses because there's no one way to make speculation that is evidence based. And it may be evidence based from previous studies, from previous literature. I mean, like I mentioned in polling data, the 2016 election seemed to have a large polling error. Did we learn from that in 2020? Well, yeah, but the population changed by 4 years as well, too. So even if we had gotten better about some aspects of polling error, perhaps polling error was reduced in 2020, actually. It was reduced this year as well, too. So it seems to have gotten a little bit better, we think, whereas the population shifted. Are people less concerned about saying who they're going to vote for? I mean, there's all sorts of reasons why it could be different, and any of those are possible. And that's exactly, you can see the problem painting myself in a corner here, right? There's no one easy way to do it. So that's what, um, when I showed you the spaghetti plots and I had to put a hurricane up because I like meteorology, that's what we would call a sensitivity analysis in our world, right? In the weather world, they call that an ensemble prediction, ensemble models, right? Each model has a set of them with different starting values. It's different starting values leads to different results. In our case, we call them sensitivity. So examining how results change under multiple missing data scenarios, right? So you could run the MAR version, run the MNAR version. There's a whole cool world of statistics that I don't know enough about that I'd love to learn more about. Maybe on one of those days I have all that time that I keep thinking I'm going to have. Like it's usually like 3 months out, always 3 months away. I just never quite make it. Um, Bayesian model averaging is a way that we compare models after the fact as well too. This is an interesting topic. David Kaplan, I've seen him give presentations about this and read some of his papers on it as well too. So when you have multiple models for data with multiple conclusions from it, how do you make sense of them? Which one seems to be more appropriate than others? It's a whole field of statistical analysis, believe it or not. So there you go. And all you wanted to know is how to impute your data, and you came to this class. And I opened you up to Oh, that's a good question. All right, so let's talk about the missing not at random process itself. The probability of missing this is related to some unseen score values itself. So remember this, we started the class thinking of this idea of a missing indicator variable. So for every observation in your data, we still grow up with the, like I grew up with this thing. There's the angel on your devil and angel on your shoulder and the devil on your shoulder. Like there's always these, or like Freud talked about like um, the ego or I don't remember the two poles one way or the other. Like there's the thoughts of good and the thoughts of evil for everything. This is the missing data indicator, right? Either your data are good and they've been observed, or they're not. They're zero. They haven't been observed, right? That's the indicator we're like looking at. So this is your possible data for each person have this indicator on their shoulder. Basically, it's the shadow variable, and the probability that an observation is missing is related to that it being missing. If I don't know about you, but I've done a few regression models, but you can't really predict y with y very much, or part of y with part of y. Right? It's an intractable situation. Right? So there is a more nuanced or detailed feature of missing not at random. Gomer and Yuan describe focused versus diffuse. This distinction I'll mention just a bit here because it helps in the sensitivity analysis. Focused missing not at random is where the missingness only depends on the unseen score values in Y itself, right? So right there. So here, the probability that a variable is missing is related to the unseen score values and any other model parameters in the missing data process, right? So an example would be unseen depression scores are the sole determinant of missingness, right? So participants with the worst levels of depression may not feel capable or may not even want to have the opportunity to talk about their depression. So therefore, they do not provide a response to you, right? It's very real, right? And absolutely, I imagine in depression research that's quite prominent too, right? That does seem like it's a problem. Whereas diffuse missing not at random gives you a little bit of an entry point into the data that you do have, right? Missingness depends on both the unseen score values and the observed data. So here, now, we have a little bit of detail as to why things would be missing. An example of this would say the patients with the worst symptoms leave, and participants with low perceived control miss assessments due to daily disruption. Right? So there may be other types of variables that show up as well. All right. The implications of both of these different levels of missing not at random, um, the distinction implies non-response is entangled with the outcome variable itself, the problem. So in diffuse processes, again, diffuse being where we have some of the missingness is dependent on some of the things that we observed. Um, generally, these are considered harder to model. In any of these things, the irony is you need larger sample sizes. So what you're telling me is the problem with modeling missing data is you didn't have enough data. Correct, but for multiple reasons, right? Um, it's potentially capable of producing greater non-response bias also than focus processes itself. And understanding the potential type of missing not at random can help guide modeling choices, but I'm going to say that in the abstract, I feel like in the cases where I've had missing data, I don't think I've ever felt confident in modeling missing not at random. That doesn't mean that you won't be in a situation that's a little bit more predictable. Like I mentioned, keep mentioning polling error because it's a heavily studied field. It's a lot of people, a lot of players, both industry, both science, involved in it, studying a very narrow problem. Why didn't someone answer the phone or answer my survey to tell me something, right? When you think about missing it in the context of the example of depression, it's a lot more complicated, right? There's a whole lot of reasons. I mean, just the idea of what the word depression means. There's no depression, right? There's all different types. And I'm not sorry. I don't even want to pretend. I am not capable of describing it, but I understand it to be much more complex than just a word depression. Let's just put it that way. Right? So you can imagine how hard it might be, but this is part of a guide. So the two modeling frameworks, again, are selection models and pattern mixture models. Both aim to mitigate non-response bias which is the name for missing not at random, right? The bias due to non-response, by modeling the occurrence of missing data itself, right? So our goal is modeling what makes it missing. They start by factorizing the distribution of the data, and now the missingness indicators themselves, Y and M. Right. So in selection models, the factorization is this. We really are looking at the joint distribution of the data and M itself, which is sort of weird because the data doesn't exist. We know what M is almost entirely. But from this, we can think about as the distribution of missing given Y times the conditional distribution of Y. So what is the distribution of missing given Y? Well, we've seen this notation given before, and it was in the context of this means this is some type of linear model or generalized linear model. So because missing is a 0, 1 variable, the indicator is binary, we can use a logistic regression to do that. Right? We literally could, for all of our data, we could go and see what is the, can we predict the probability an observation was actually missing based on their Y values. Similarly, then we have the distribution of Y itself. So that's like an empty model of Y. This treats missingness as an outcome that depends on Y and potentially X as well too, if you have X involved. And it's similar to statistical mediation in this case as well, right? Whereas like Y might be a mediator between X and the missing process itself. And if you remember way back in the beginning of class, I took screenshots of pictures of the book where it described initially the missing not at random processes, and it had these variables, almost like a when I'm looking for a graphical model of what was happening. We had Y, we had the missing indicator, we had X, right? That's sort of where this process, when he starts talking about mediation, is playing out. Pattern mixture models work a little bit differently. Here, we're looking at the distribution of Y given M, right? That's really weird. Actually, sorry. We're still looking at the joint distribution, right? But now we're looking at the distribution of the observed variables given the pattern of missing. So that's weird, right? But you remember that box that mice gave you, that table that had the different colors for which patterns were existing in your data? You could think of it this way. For each one of those patterns, take your outcome of the variable of interest, Y, and compute its mean and variance. Right? Is it different for each one of the patterns? That's what we're looking at here, right? And so now this model sort of flips the script a little bit. It says, how is this variable in each? Now, I will tell you one of the patterns, or some of the patterns, you're not going to be able to tell that, right? So imagine we have three variables, Y, X1, and X2, right? We have potentially 8 patterns of missing, right? One where they're all missing. Those are undistinguishable from people who are not in your study, right? So 7 where at least one variable is observed. But of those 7, only 4 are going to have Y observed, right? So you have to look at Y for those 4 themselves but that's sort of the hard part, right? What is the distribution of Y when we didn't observe it? And how do we go and predict what that should be? So this is similar to moderation or group comparisons, right? So the key difference between these approaches are both are trying to describe the same joint distribution, Y and M jointly. So the outcome of interest and the missing process, or the missing indicator, right? And so why you can have this approach mathematically, right, where M given Y times Y, or Y given M times M, is that both of those factorizations lead to the same joint distribution. So you've got a joint distribution that you're trying to approach and handle, but one way is Y given M to begin with, and one way is M given Y. Does that make sense? Sort of? Um, the difference, though, is that they require different inputs and assumptions. Right? And for the same data, you can get different results, right? So furthermore, the sort of the conditioning model itself, so this first part of the factorization, or this first part of the factorization, is telling a different story. You like that word? A different, it's sort of using a different process involved, right? So in selection, missingness is the outcome, but in pattern mixture, missingness is the thing that you're using in prediction, right? And the problem of it is either or both could be plausible in any situation. So, selection models for multiple regression exist. There's some work from good old 1970s working on sample selection bias. The idea was that you take the focal analysis model, in this case a linear regression, with an additional model for the missing data indicator, right? And so this typically will use maximum likelihood or Bayesian estimation with factor regression. The original two-step method, we've gotten better at estimating things since the 1970s. So we do at least something better. And here's basically how it would work. And the missingness model, if we use a probit instead of logistic regression, why am I going to say probit? Is anybody going to take a guess as to why instead of logit in this context? Because probit leads us to allow us to do that trick to have underlying continuous, the latent response, but logit doesn't. Probit, we use the reason why we can use a truncated normal distribution in probit is because probit assumes this normal ogive underneath the process. It also has a constant variance. The variance is 1. And so this M star term is the underlying continuous latent variable. And oftentimes, the book author is very fond of this approach. But again, you don't have to use probit. You don't have to use this, but this is a way of looking at it. M star is the underlying latent variable. Again, there's that term. I would call this an underlying continuous response representing the propensity for missingness. Right? So what that means is the following. I haven't done some drawing in a while. How about some drawing? Right? So here, in that case, we might have M star on the values of M star on the x-axis. 0 is always the mean. And then you have some distribution here. This is the propensity to miss. And so now if we added a cut point tau to it, any M star that's on this side over here is where M equals 1, and any M star on the other side is where M equals 0. And the way that the probit works is the probit allows us to assume that thing follows a normal distribution. There's no way we can estimate its mean. There's no way we can estimate its variance, right? Because it doesn't exist. But we can use it synonymously with the binary response, so long as it's a probit model. Does that make sense? Yeah. Mhm. Great question. I picked random uniform. So the random uniform actually, what you ended up doing in random uniform. So in each of the steps, if you followed my example in class, which is where I was trying to get you to do to make missing, what you came up with was a model for missing data on a basically giving each observation the probability that is missing, right? So what you want to do for every one of those observations is simulate that same probability. You need to give them an equal chance. So a uniform distribution does that really well, because let's say the probability is zero point 0.7. A uniform distribution, standard uniform, goes between 0 and 1. If you draw 100,000 values of that uniform distribution, you will find about 70% will be less than zero point 0.7 because they're equally likely across the distribution. So we use that there because our only goal was to represent yes or no. There are other ways, of course, of doing that as well too. We could have translated that probability of zero point 0.7 to a z-score and drawn from a random normal. That would have achieved the same purpose, random standard normal. Does that make sense? Yep. Okay. So the missingness model basically has this underlying continuous variable. There is a threshold. In this case, the threshold is usually fixed at 0 because we cannot identify this continuous variable. And the residual variance is fixed at 1. Again, this is due to the probit itself. Right. And so the focal model, the standard regression may look like this right here, where y, the outcome of interest, is being predicted by x. Let's just keep this not multi-level. After the last couple hours, doing this in multi-level will make my head explode. So if you're in multi-level and you have it missing not at random, just forget it. Just go find a different degree, go quit your job, go into like the Peace Corps. The world could use you right now, right? So never mind. I'm just kidding. It's really difficult. Or be like me. I love the challenge. I really do. That just means I'm acutely aware of all the failures that goes with trying to feel to hit a challenge. But I feel like I grow. Failure is a growth process for me. Grown a lot over the years. Anyway, the missingness model. M, right? Only the dependent variable predicts the missing under this framework. This is the framework that was pitched by Heckman back in the day. So now, if we could observe the missingness indicator as a continuous variable, this would just be another straight continuous regression. Technically, you don't need this. That just fits the underlying continuous or latent response thing that our author seems to love going throughout the book. So again, missingness only depends on the value of the variable that's missing. This is the framework that is, I'm blanking on it now. This is a focused MAR process, right? So that is what is guiding that term, focused MAR, right? All right. So similarly, you could then go and say, um, you could add a diffuse model. You can change this from focused to diffuse if you then predict missing with not only y but also x itself. I think in this sense, to me, this is a more valid approach. If you're going to use this approach, put all the variables in to predict missing. I think that the idea of focused is a strong assumption, but it's testable, right? It's testable by whether or not this coefficient gamma 2 is 0 in this case. Right? Now, the important assumptions here are the residuals of the focal model, and the missingness model must follow a bivariate normal distribution. This is strict and testable, right, itself. The other assumption is that we correctly specified the missingness model. Right? Missing here is caused because of y, or in this case, y or x. You may have a functional form of y as well, too. It may even be more complicated than that, right? I can imagine a mixture of y. For some y's, no missing. For some y's, maybe missing. Whatever those are, right? And like everything else that I was talking about with missing not at random, omitting important predictors will introduce bias. But how do you know you even have the right predictors of missingness in this case, right? I think you could, yeah, well, I was going to map this onto my polling error example, but I think we could talk about that actually a little bit, right? In the 2016 presidential election in the United States, it seemed like polling error were related to personal characteristics of some of the folks who were being polled and indicated and sort of made them more suspicious of answering a phone call from a random number. And that tended to be related to certain people that they would vote for. It's a rough, non-scientific way of describing it. They're probably somebody who's an expert on it will tell me I'm wrong in 15 ways, but just go with that story to help you see the process. What do I mean by that, though, is the following. If you didn't realize that was happening, like we didn't when that election cycle was happening, you saw the result. We missed on who would be likely elected to be president or who would be elected to Congress or represent us as a country, the United States. So it was only through hypotheses and other research where we could try to even try to address it. But that's part of it. All right. So how these models mitigate bias is through, again, factored regression. Because now we are really looking for the distribution of y, m, and x jointly, but we can factor that into the distribution of m, conditional on y and x, times the distribution of y given x, which is really the focal model that we're after, times the distribution of x itself, right? And so here, the key is how the model defines as the distribution of the missing values. themselves. And this distribution becomes both, like you've seen in the other factored regression approaches, the distribution of y conditional on m and x involves the missing data or the missing indicators as well too. And so what's end up happening is that when this process plays itself out, if our selection model for missing is appropriate and approximately correct, we're adjusting the expected value of y based on those model parameters themselves. So now our missing data model for missing out at random allows us to adjust our parameter estimates the same in a way that would be more consistent with the missing data itself. Right? How's that work? All right. So here's some recommendations. Diffuse models are harder to estimate and may require a larger N than focus models. We know that. I was just joking. The irony about missing data is you need a lot more of it. Right. Sorry. I think that's funny, but nobody else does. I'll take your hint. You know, I used to believe jokes would get more funny if you keep telling them. So I may have to next week. All right. Never mind. Specification, while omitting important predictors is generally worse, overfitting could also be a problem, right? Because now think of this. Every time you build a really complex model based on features of your data, you have a problem with the garden of forking paths potentially, right? The idea of model choices based on things that your model is telling you. There's no different here too. But now what's happening is your adjustment for missing is adjusting what your sample size happens to be, which affects power and precision potentially. So overfitting can be a problem too. So how do we build a model? I think you start with a focus model. So you model of interest, y equals x in this case, and add prudential predictors, especially those from the focal model or strong auxiliary variables, and going at them stepwise. At least that's what Ibrahim and colleagues had suggested. The diagnostics are carefully inspecting parameter estimates and standard errors. Watch for large increase in standard errors compared to missing at random models. That's the impact of the missing data assumptions at play itself. Or implausibly large R squared values for the missingness model. Isn't that great? My R squared is 0.9, and I had 60% missing data. But that is also a hard standard because if you truly do have a big effect, missing data may weaken the influence of it. And of course, there will be convergence issues because there always is. Isn't that right? Sorry. Just thought I would sprinkle in some of the conversations I've had throughout the year. Right. All right. The other approach is pattern mixture modeling. Pattern mixture modeling is aligned with moderated processes, right? This is how missing data moderates the impact of the relationship of variables in your model. The core idea is to define subgroups based on missing data patterns, completers versus those missing Y. Estimate model parameters within each pattern, and then compute overall marginal parameters as a weighted average of pattern-specific estimates, right? So in this case, if we had two patterns of missing data, it might be a blend of the proportion of people with 0 times the mean Y of 0 versus the proportion of people of 1 times the mean Y of 1. In this case, you're going to say, wait a minute, if Y is missing, yeah, that's not for Y, if X is missing for some of these, right? If you have missing data on Y, you won't be able to estimate that parameter right there, the mean of the missing. How would you know what that happens to be? And this is the challenge, estimability. For patterns with missing data on Y, parameters involving Y cannot be estimated from data for that pattern, right? So when Y is missing, you can't get the mean of Y. You can't get an estimate of the variance of Y. So either you have to provide plausible values for those inestimable parameters, or you have to put additional restrictions, identifying restrictions for borrowing information from other patterns. Still not good, right? So here's an example. Using the missing data indicator 0 or coded 0, 1 as a moderator, right? So if you think about it, what we could do is predict Y based on whether or not a person was missing on y, and what x happens to be, and then potentially the interaction between the two. Why I say that is when m is 0, right, you get beta 0 and beta 1x. Uh, when m is 1, you get the intercept being the sum of these, and the slope being the sum of the beta 1s, right? Um, Alternatively, you may also not use the interaction. This is what's called focused, but it's difficult to be able to do that because here, in either of these models, like I just said, if m is 0, you cannot estimate. Um, I'm sorry, if m is 1, if the data are missing, you actually cannot estimate these parameters. Right? The same thing with a single m. Um, so if you really want to identify inestimable parameters, people have come up with, and it's bad in statistics when someone calls it a heuristic, right? You know the difference between an algorithm and a heuristic? You heard those terms? Algorithm is like a straight process, identifiable, transparent, step one to step whatever gives you a result, right? Heuristic is fuzzy. Here's a guide. May not always give the same result, may not always have the same process. Here you go. This is a heuristic. This is a heuristic. That's code for saying, well, we got to do something. Okay? And we're going to do this. Does that make sense? That's my take on it. Maybe not the book may not use so many words, but that's the way I look at it. So here, you could use standardized effect sizes as a guide potentially. You could talk about the intercept difference, right? So what you have to do is specify a plausible standardized mean difference. Now many of you may work with Dr. Aloe. I know he does standardized mean differences. Did anybody work with standardized mean differences in any of your work? Okay, great. What's a plausible distribution? What's a plausible standardized mean difference? Come on, Ju Young, I need to know. You see what I'm saying? You don't have to answer that. Well, what I say is this. Okay, so standardized mean differences. We know that to mean there's how many standardized units are two means of two groups apart. Would we describe it that way? So now, what is a plausible standardized mean difference? Well, I don't know. 0 seems pretty good. Would 1? Yeah, one standard unit, one standard deviation away in means. Maybe I'm interpreting that wrong. I'm not an expert in standardized mean differences. Please talk to Dr. Alloway if you know him and about this. The point I'm trying to make is here's where the heuristic comes in. It's telling you to plug in a number for the mean difference. I've seen this before. It's called grant proposals. Now, Lisa describes her time at KU as only doing grants. Well, she worked half in a center where people were submitting grants, an institute, a lot of them. And so she did a lot of analysis plans. And there was one that she created where the investigators, it was for Institute of Education Sciences. So we're going with this. May that be resuscitated in a future presidential administration. We need IES. But this is a funny story to me because the grant proposal itself was constrained in how many schools could participate. And it was something like 12 or 10 schools. And this is a school level fix she was going with. And of course, it needed the power analysis. So normally the power analysis, the variable that you're manipulating is the number of units, n, in this case, number of schools. But that was fixed. So she tried a different approach that said, how large of a standardized mean difference would be needed for this to be significant under this sample size? So the flip of it. And the answer was, I think, seven units, 7 standard deviations. That seems implausible. Well, the folks that read that grant thought that was a great approach and funded it. So, but you see what I'm trying to say with this, though, right? This is what is a plausible value of a mean difference? I mean, if you think about a normal distribution, something 7 standard deviations from the mean, do you know how many draws from a normal distribution you'd have to do before you found a value 7 standard deviations away? It would be a long time. You might be here a while. Let's put it this way. The PhD you're working on is going to look small comparatively, right? It's not impossible, highly improbable. Anyway, so that's the first thing. Basically, if you specify this mean difference, D, then you can try to estimate what the actual difference of effect is. But guess what that depends upon? Oh, wait, you have to get these values from a preliminary analysis. So these numbers come from the wrong approach, and this one you just made up entirely, and that is why it's called a heuristic. How bad do you want your paper published? You want tenure? Guess what? My mean difference is 3. Never mind. You know, see what I'm saying, right? You have to have a crystal ball to figure this out. You have to be clairvoyant. Same thing with the slope as well, too. All right, what are the assumptions? The assumption is the correct specification of the pattern differences. Yeah, good luck with that. Um, I'm like my assumption meter, that one is implausible. I'm just going to, I think I need to do that for all the assumptions of the model. Normally distributed error? Yeah, that seems pretty good. It's very robust. My D is 7? No, I don't even know I can rotate anymore. That's the wrist that I broke earlier in the year. It's harder. Anyway, transparency is another problem assumption. Unlike selection models, assumptions about the missing data mechanisms are explicit in this process, at least. Um, and then pooling, to get marginal estimates, you have to pool. You have to get basically pattern proportions and then somehow mix them together. That one's less hard. The pooling's less hard. The problem is what you're pooling for parameters. Impossible, right? And then you can do pattern mixture models for sensitivity analysis. You can basically um, go about trying to figure out what the correct value. So you try different values of that. Oh, let's try 7 standard deviations. Great. Let's try 6. Let's try 5. Good luck, right? My guess is the sensitivity analysis would reveal the answer is, yeah, it's quite sensitive to the choice of D, but that's only a hypothesis. So, in summary, what do you think of missing not at random? This is just a couple of the options. I've seen other options as well where people actually come up with more specific models for the selection approach, right? Really build in why something is missing to try to then figure out what it would have been what the missing data would have been otherwise. My personal, I like the selection approach a bit better, but I still have problems with all of it. What do you think? You like it? So wrapping up for today, if you're going to have missing data, don't. That's what we've learned. But especially don't if it's multi-level missing. Oh, really bad. Or missing not at random. Right? Today is the nah, sounds good, right? Things we have to do to get through. But knowing a little bit about that will help you as you try to publish papers with missing data or otherwise investigate it. And absolutely, like the things that you see here that are unsatisfying to you about why we can't get this done this way or that way, if you're looking for a research topic, here you go. There's a lot. Well, there's a lot of people working in missing data, but there are a lot of questions that we haven't been able to answer yet. So pretty decent. Any questions for me about anything I just mentioned? Yeah. hmm use a multivariate, multi-level model in JAX. That would be my version of it. You may also come up with a more instead of using a model base, you might be able to use that same approach to build a maximal model that does imputation through JAGs only. And then once those imputed data sets are done, you may be able to use those completely like in a missing data process. That might be so basically what I didn't talk to you here, like the book describes mice as using Bayesian or using MCMC. They didn't say Bayesian. The process of mice is a Markov chain, but it's every individual step may or may not use Bayesian estimates. In fact, what I understand mice to do from a default is use maximum likelihood estimates for every one of the chained equations. But the process of the chain, where one iteration depends on values from the previous, still a Markov chain. You can use Bayesian for full-on imputation if you need to, right? So what I'm saying is you can come up with a multi-level model, maybe a maximal model, where you put everything in that you have in your data, and you treat each of the level one variables as having level two components, or whatever the nested structure is. And the whole purpose of that is only to give you the data sets that are imputed. And then those data sets that are imputed, you may then go and put into the pooling or the estimation and pooling phase of the multiple imputation. I could see that being a straightforward. Alternatively, now let's take some hacking of JAGs. I've done it before. It's kind of fun. You could do run JAGs model to give those data sets, and then impute, maybe take 100 of them and bring them into JAGs to your analysis model, but have JAGs sample which one to use for each iteration. There's a way to have that happen too. So there's a way you can do pooling and MCMC at once. But why I'm saying that, like, what I'm trying to tell you about this is the answer to a complex multi-level or a missing data problem might come from different features of multiple of the methods that you see in this class. But I don't know that, and that may lead to other research as well too. I mean, there are people that may have already done this as well. Does that help answer your question? Yes. Yes. No, I will not include this or next week in the final. Okay. So if you love psychometric data, if you love test scores, if you want to talk about plausible values, next week. Let's talk plausible values next week. I'll put up a couple papers on Icon that are, one is a 1992 paper that I actually list as one of the more seminal works about understanding how to do stuff with test data. By the way, it's funny how many of our vendors use it. I don't believe many, but certainly NAEP runs on it. So this is an important part as well. NAEP, the National Assessment of Educational Progress here in the United States, which I believe is still going to continue in some form at the moment. All right. Thanks, everybody. Have a great rest of your Thursday. You know where to hit me up on an email. By the way, office hours next week, same time as normal, 10 to noon on Wednesday. And the same thing for finals week as well, too. Okay? Actually, 10:30 to noon finals week. All right. Thanks, everyone. Take care.